Hello and welcome, class, to another lecture here as we work our way through Burge and Overby's 4th edition, Chemistry Atoms First, where now we are entering Chapter 4. In our previous chapters, namely in our most recent previous chapter, Chapter 3, we discussed the nature of electrons. So the wave-like nature of electrons, the orbitals that they inhabit, etc. Where we are going to be moving next now is taking those electrons and using them to understand the reactivity and nature of atoms. Different forms of atoms, right? The different elements. How are they characteristically the same? How are they characteristically different? And we can use electrons and how they arrange themselves inside of atoms to really understand and answer that kind of question. All right, so without further delay, without further ramble, we're just going to jump straight into it. We've got a lot to talk about, so we're going to try and stay focused here. Electron configurations, what are they, and how can we use them to understand the natures of atoms? Well, I'm going to be building off of an analogy that I was using in Chapter 3, Part 4 lecture. If we consider the quantum numbers that are used to describe electrons, the n, the L, the M sub L, to be referred to as the city, the street, and the home address where electrons live, then we can get a pretty good idea for like how these different quantum numbers interact with each other, how they're used to describe the energies, the shapes, the locations of these different orbitals. And in addition, we also introduced the notion that the electrons are then considered to be the occupants inside of these houses. Well, all atoms can occupy multiple electrons. These we call multi-electron atoms. It's a pretty straightforward name, right? Multi meaning multiple. We have multiple electrons in these atoms, aka houses. Well, we're going to build off of that analogy, as I just said, and the new addition to the analogy is that if these electrons are quote-unquote living in these houses, then the houses are also going to have to coordinate in order to construct the atom itself. Now, the coordination of the electrons inside of the atoms can be understood via the 3 rules listed down below that we are going to discuss: the Pauli exclusion principle, the AUFBAU principle, and Hund's rule. In the greater scheme of our analogy, we can think of these 3 rules almost like the 3 rules of the HOA of the atom, right? The homeowners association. It controls the suburbs. It helps to lay out the rules so that everyone's on the same page, what to expect as you live in the suburbs, as you need to coordinate in the suburbs because everyone's right next door to each other, as we can kind of see in the illustration here on the right. So as each of these electrons fill the houses in these suburbs, we're going to have to pay attention to these 3 rules to really be able to understand and predict how the electrons are going to behave. All right, so the first of these 3 rules is the Pauli exclusion principle. So we're going to discuss these 3 rules first and then use them to understand how the electrons are going to start coordinating inside of these larger atoms. So the Pauli exclusion principle states that each electron inside of an atom is going to have a unique set of quantum numbers. Unique set meaning that no 2 electrons in an atom will have the same set of quantum numbers. It is physically impossible. The implication of 2 electrons having the same 4 quantum numbers is that the 2 electrons are literally in the same space at the same time, and that is physically impossible. All right, so one fallout of this rule, though, is that you can only have 2 electrons per orbital because of the Pauli exclusion principle. To get a really good idea as to why that is, we are going to address what the quantum numbers are for electrons that exist inside of the p orbitals, this p subshell. So we've already done this type of example once, but now we are doing it again with a different twist, a different perspective. All right, so assuming each of these are p orbitals, let's say they're 3 p orbitals. So they're a little bit higher in energy. The n for each of these orbitals is equal to 3. The L is going to have to be equal to 1. And we've discussed this already in Chapter 3. If you're working with a p orbital, by necessity, you are working with a quantum number of L equal to 1. And that's going to be true, again, for each of these orbitals so far. They're each a 3p orbital, therefore they each have quantum numbers 3 and 1 in the first two positions. The third quantum number is where we define the orientation of these 3p orbitals. So we can see one of these is along the x-axis, one lies along the z-axis, one is on the y-axis, and as a result, each of these three different orientations is unique, at least in 3D space. The quantum number that we're going to use to describe each of these orientations is going to be the -1, 0, +1, m sub l quantum numbers. So -1, 0, +1. And I am going to, let's see, how do I want to organize this? Like this. All right, so each of the quantum numbers or quantum number sets so far uniquely define these three different orbitals. Because the third quantum number is different, we can see, again, we have three different orbitals we're working with. The fourth slot pertains to which electron we plug into the orbital. And there are two different options, right? Again, either we can have the +1/2 case or the -1/2 case. And that's true in each of these orbital cases. We could have the +1/2 or we could have the -1/2. +1/2, -1/2. So there are a grand total of 2 electrons that we can put inside of each of these orbitals and still have unique quantum numbers. AKA, we can have a total of 6 electrons in the p subshell without breaking the Pauli exclusion principle. So we're covering a lot of rules here, but again, these rules don't come out of nowhere. We're not arbitrarily making this up. This is observationally true. We have never found 2 electrons with the same sets of quantum numbers in the same place. It is physically impossible due to the constraints of how matter functions in our physical world. All right, so the p subshell can have a total of 6 electrons, each of these electrons with a totally unique set of quantum numbers. The next rule is the AUFBAU principle. This principle states that electrons always occupy the lowest energy orbitals that are available to them. Now in energy, we have listed here the diagram going from low energy down below. So we have low energy here. We can see the energy increases along this y-axis until we get to high energy spaces up on top. And the organization, like what is actually being organized here, we can see down below there is a little dash line, a series of underscores, like this little blank that is labeled with a 1s. And I realize that that yellow is a little hard to see, so I'm just going to relabel it. It is a 1s little marker here. And what this really represents, this little flat line, is the orbital. So it's a little bit nicer, a little bit easier to represent the orbitals just with these little flat lines, signifying that electrons could be placed here. It's currently empty. There's nothing on top of this little flat platform, but it's easier than trying to literally draw the actual orbitals every time. So we have the 1s that's listed down below. This is the lowest energy option. So if you're working with an empty atom and you need to add a certain number of electrons to this atom, just like when you pour milk into a glass, the milk fills the glass from the bottom to the top. If we need to pour some electrons into this atom, the electrons are going to funnel their way down all the way to this most low energy space down here, this little 1s orbital that's right here, low in energy. Now again, there are 2 electrons that we can put into each orbital. So there are 2 electrons that we can draw inside of each of these, or on top of each of these little platforms. So the way that we represent these electrons, the upspin or the +1/2 electron, we always represent with an upwards arrow, and the -1/2 or downspun electron, we always represent with a little downspin or downwards facing arrow. So if we needed to add, let's say 5 electrons into this atom, well, we would pour all of our electrons in, they'd funnel down to the bottom, and they'd start then filling the glass. So after filling one particular orbital, we're going to want to move to the next available orbital that is still low in energy. So we're going to place our next 2 electrons here. And I'm going to start drawing my electrons as half arrows, just because it flows a little bit nicer, it's a little bit faster. But whether you draw half arrows or complete arrows, it doesn't really matter. All right, so we've added 4 electrons, and again in this hypothetical I said let's add a 5th. Well, the 5th electron we can see after the 2s in energetic space comes the 2p, so we're going to put our 5th electron right here. Doesn't really matter which of these 3 little platforms you put it on, since each of these platforms is equal in energy, the 5th electron could go anywhere. So again, this is the AUFBAU principle, the principle that states that we are going to go from low energy space all the way up to high energy space, all depending on how many electrons we need to fill. We can use this diagram to see after the 2p comes the 3s. We're just going in order of low energy to high. Then it is the 3p. And we can actually see here, even though 3d, like the 3 is consistent, it's actually the 4s that is the next lowest in energy. This is going to have some pretty important implications, but the one that we're facing right now is the recognition that we actually fill the 4s orbital before we fill the 3d. So we go from 3p to 4s to 3d to 4p to 5s, etc. And here's where like the diagram kind of trails off a little bit. So this is going to be the order with which we fill these orbitals. This is the arrangement of lowest energy to high energy. But we don't always draw our electrons out from like low energy space to high energy space using diagrams like the one that we just saw. In fact, again, we always try to find paths of least resistance. We're always trying to find the easier approach to whatever it is that we're trying to do. We're humans, we're kind of inherently sort of lazy beings, and we want to be able to minimize the amount of work that we have to do. So in place of drawing out that type of diagram that we just saw in the previous slide, we're going to now introduce what we call orbital box diagrams. So the thing that this approach has in common with the previous slides demonstration of orbitals and their relative energies is that we're not going to literally draw every orbital. If we wanted to draw every orbital, it'd take up a lot of time. Here's the s, here's the p in one direction, here's the p in another direction, etc. And the organization ends up being like really messy. So we do not take this approach. What we do instead is draw a box. Right? Any old box will do, square, rectangle, whatever. And what this is meant to represent now is an orbital. The way that we can label or represent this orbital a little bit more explicitly is to write what it's supposed to represent. So let's say we're drawing the orbital box diagram for hydrogen, which only has 1 electron. Well, we're going to draw this box, and the box that we draw first is going to represent that lowest energy state according to the AUFBAU principle. This is going to be a 1s orbital box. So yes, even though the s orbital looks like a circle, we're just going to draw it as a box, label it with a 1s, with the understanding that this is supposed to represent a sphere around the nucleus. Now hydrogen has 1 electron inside of it, wherever it's going to be. That low energy 1s electron, we're just going to place it right inside the box. All right, now this is the orbital box diagram for hydrogen. It is the simplest case of all of the electron configurations in terms of drawing an orbital box diagram that we could draw. So let's make it a little bit more spicy. All right, let's turn our attention to lithium. Lithium has 3 electrons, and we need to know where we are going to place these 3 electrons inside of the lithium. Now the lithium is going to start in the same place as hydrogen. Again, according to the AUFBAU principle, we always start with the lowest orbital first, and we are going to fill it before we move on to starting to place electrons in any higher energy orbitals. So since lithium has 3 electrons, we're going to place 2 of the electrons in this box, and the third we're going to have to move on to a new box. Right, again, if we're thinking of these orbitals like houses, we can only have 2 roommates per house. It might be more appropriate to think of these as like dorm rooms, since we are in college here, and you can only have 2 roommates in a dorm. So we're gonna be rolling with this example. All right, so the question is, how do you label this next box? What is it supposed to represent? Well, in order to answer that question, at least for now, we're gonna turn back to our diagram on this page, and I'm gonna clean it up a little bit just so it's a little bit fresher, it's easier to read. We currently just filled the 1s box. We are going to have to move on to the 2s box next, right? So that's again what this energy diagram is meant to represent. So this is going to be a 2s orbital, and we are going to place 1 electron inside of it. So whether we are working with something that's more along the lines of Bohr's model, where we have some nucleus in the middle, 2 electrons in the 1s, 1 electron in the 2s, so this is our 1s, this is a 2s, or if we are trying to draw something that's a little bit more like the modern atomic model with our more spherical, let's say, shapes around the nucleus. So this is supposed to represent a sphere. I remember from art class, like, whoop, something like that. So this is our sphere, and it's going to be kind of hard to like illustrate, oh, here are some electrons somewhere inside of this like spherical shape, let alone having to add the 2s and another layer of sphericalness to the picture. I mean, you can already tell it's very hard to see where the electrons are in this picture. So whereas the modern atomic illustration is more accurate to where the electrons could be in 3D space, if you're trying to draw it by hand, it can be very difficult. And for that reason, it's going to be much easier for us to illustrate where the electrons are using this more simplified orbital box diagram approach. So it's important to recognize as we continue to use these orbital box diagrams and get more into discussing the electron configuration, don't forget what these are supposed to represent. Each of these orbitals are layered on top of each other, all of them centered around the central nucleus. It's just difficult to keep drawing it this way. All right, our last but not least, the third of all of our electron configuration rules is known as Hund's rule. This rule covers our bases for when we are working with what are known as degenerate orbitals. And what the rule states is that electrons placed in these degenerate orbitals are going to spread out. We're going to maximize the number of all of the unpaired electrons. Now, what does it mean to be a degenerate orbital? Degenerate in this case means equal energy. So if we turn our attention, I'm just going to go back a couple of slides. If we turn our attention back to the AUFBAU principle slide, the 1s orbital, the 2s orbitals, each of these only had one platform above the label. But when we turn our attention to the 2p's or the d's or even the f's, we can see that there are plenty of platforms that are equal in energy to each other. So each of these 3 individual 2p orbitals are equivalent in energy. They are degenerate. Each of these 3d orbitals are equal in energy. These are degenerate. Each of these 4f orbitals is equal in energy to each other. These are all degenerate. And we can pick out a couple of others on this slide, but you get where I'm going with this. At least I hope you do. Each of these individual subshells have degenerate orbitals. They are all equal to each other. And so for that reason, if we're trying to place electrons inside of a degenerate subshell, like let's say these 2p orbitals here, what Hund's rule states is that we're going to have to spread out the electrons across these degenerate orbitals before we begin stacking them inside of the same orbital space. So a good example of when Hund's rule is going to apply is if we increase in complexity again a little bit and we draw the orbital box diagram for something like carbon. Now carbon has 6 total electrons inside of it. 6 total electrons. In drawing the orbital box diagram, we're again going to start with the lowest of the low energy, the 1s orbital, and we're going to put 2 electrons inside of this box. This means that we still have 4 electrons left to place, and just like how we did with lithium, we observed that the 2s orbital is the next highest in energy, and we're going to place 2 electrons inside of this box as well. This means now a total of 4 electrons have been placed, and we still have 2 to go. According to the AUFBAU principal energy diagram, after the 2s comes the 2p. Well, the 2p subshell is a 3-for-1 deal. You get 3 individual 2p orbitals. Even if you don't need all of them, you should still draw each of them. This is going to be important. The reason why it's important is these last 2 electrons, when it comes to picking and choosing where they're going to go, each of these 3 houses, each of these 3 dorm rooms are the exact same. Perfectly the exact same in every single way. And so it doesn't make sense to try and shove 2 electrons into one house when all of the houses are the exact same. They are of equivalent energy, and there's no reason for the electrons to try and shove into the same space. They are going to spread out. So long as the electrons are in degenerate orbitals, we are going to try and maximize the number of unpaired electrons. So we can see that we went from allegedly maybe having 1 single pair to now we have 2 unpaired electrons. This is the greatest number of unpaired electrons we can have with 2 electrons moving into these boxes. All right, so this would be the orbital box diagram for carbon with its 6 electrons. We'd have 2 electrons in each of the most low-lying subshells, and then 2 electrons in this 2p subshell spread out as much as they can be. All right, so those are our 3 HOA rules. Those are the 3 rules that govern electrons as they start filling up atoms, as they start coordinating with each other, moving into the suburbs, building the atom. And so to tie this, the rules that we have now learned drawing these orbital box diagrams back to our previous lesson from chapter 3, where we ended everything with quantum numbers. Again, each of these electrons inside of our carbon should have a unique set of quantum numbers. So let's just pick out this electron right here. Well, we can draw or list each of the quantum numbers that corresponds to this drawn electron. Since we know which orbital it's in, it is in the 2s orbital. This means that we know what the quantum number n is, and we know what the quantum number L is. Our n is equal to 2, and our L, because this is an s orbital, has to be equal to 0. Now the m sub L we can intuit just from looking at the boxes and also knowing what our L is equal to. L defines the range of acceptable and valid m sub L values that we can have. Well, the range goes from negative L to positive L, which means the only valid m sub L for this particular orbital is also a 0. Last but not least, we can look at the electron. It is pointing up. If it is pointing up, it is going to represent that positive 1/2 electron, and there we go. We know the city, we know the street, we know the home, and we know exactly which electron we are referring to. This is the upspun electron in the 2s orbital with the quantum number set 2, 0, 0, plus 1, or plus 1/2. All right, so with that in mind, let's take what we have learned so far and apply it to an example problem with even more complexity. I would like you to draw the orbital box diagram for the 15 electrons in the element of phosphorus. In addition, in much the same way that we just did with carbon, I would like you to pick out what are the 4 quantum numbers of the 15th electron that gets placed into phosphorus. All right, welcome back from unpausing. I hope you actually attempted working out, illustrating what the orbital box diagram for this phosphorus was and determining what its quantum numbers were, at least for that 15th electron that gets placed. So let's just do this together. There are 15 electrons inside of phosphorus, and each one of them is going to need a home. So we are going to start with the lowest of the low, the 1s orbital. We're going to take 2 electrons, put it into the box. After that, we have the 2s orbital. Similarly, we're going to take 2 electrons, put them into this box. So far, we have placed 4 of the electrons, and we have 11 left. Well, after the 2s, we get that 3-for-1 deal. We get all 3 of these 2p orbitals, and we're going to have to place 6 electrons in each of these orbitals. 1, 2, 3, spreading them out first, and then 4, 5, 6 inside of each of, or 2 electrons inside of each of these boxes. Well, after 2p, if you didn't pause the video or scrub back to see the AUFBAU principle diagram, which again I'm going to clean up, boom, we've placed 2 electrons in the 1s, 2 electrons in the 2s, 2 electrons in the 2p, and we can see in our diagram next what comes is the 3s orbital. Oh, too far. Here we are. Spoilers. All right, so the 3s orbital is what comes next. 3s box, 2 electrons inside. So far we have placed 2, 4, 6, 8, 10, 12. Suddenly I just couldn't count by even numbers. 12 electrons placed. This means we still have 3 left that need a home, and after the 3s in the diagram, if we were to look back, we would see comes the 3p. Now, much like the 2s, the 3p is also a 3 for 1 deal. We're gonna have to draw each of these 3 empty boxes, even if we end up not placing an electron in one of the boxes. It's just a great habit to get into. All right, so our 3 electrons, we have 3 left. Each one of them, according to Hund's rule, we are going to spread out as much as we can. Each of these last electrons spreading out in the degenerate orbitals, each one getting their own identical but separate homes. All right, so hopefully this is also what you got. You probably had more space to actually draw the 3p up right next to the 3s, but again, I write large, so I ran out of space. The last thing that we were asked to do was to identify the 4 quantum numbers of this 15th electron, the last one that was placed in all the boxes. So I'm going to draw that right up here. Now we are going to follow, again, the N, L, M sub L, M sub S format. So first and foremost, we need to identify what shell the electron is in. In order to figure that out, all we have to do is look at the label on the orbitals that we're working with. 3p means that we are working with a 3 for the N and a 1 for the L. Now the M sub L, this is again supposed to represent the orientation of our orbitals in 3D space. Which of the 3 you choose doesn't quite matter, but by conventional standards, when we're working with the p orbitals, we label the M sub L is equal to -1 as the first box, the 0 is the central box, the +1 is the third box. So again, since each of these are degenerate, it doesn't really matter which of these 3 you choose, because they're just relative or unique relative to each other in 3D space. But just by conventional standards, we're gonna stick with that third box being equal to the +1 label. Now, last but not least, the electron spin, we can see the arrow is pointing up. And again, this is technically a conventional standard that we draw the upwards facing arrows first. By all means, this could be like each of these 3 could be downwards facing, just so long as each of them are the exact same. It doesn't really matter. But according to conventional standards, we draw +1/2 electrons first, and then the -1/2 come after. All right, so our unique quantum number set for the last electron is 3, 1, 1, 1/2. All right, so we've seen our 3 rules. We've been using and utilizing our 3 rules just to be redundant. And even when it comes though to drawing those orbital box diagrams, which was a simplification of being able to illustrate where the electrons are in these multi-electron atoms, even then it takes up a lot of space. So the shorthand of the shorthand is what we're going to be learning now. These are known as the electron configurations. This is a shorthand notation for representing the location of an electron in an atom, right, as they fill atoms. The notation follows this pattern where we have the orbital listed first, so the shell is the 1 in this case, the subshell, your orbital, your quantum number L comes next. This format we've been seeing so far for labels for atomic orbitals, so this hopefully is not too scary, is not too unfamiliar. What is new is what is placed in the superscript. This represents the number of electrons that are inside of that particular shell and subshell combo. So what this is representing, this 1s2, this is equal to what we just drew. There are 2 electrons inside of the 1s box. These 2 things mean the exact same thing. They give us the exact same information. So we can use the electron configuration notation to also illustrate how many electrons are where inside of our phosphorus atom. So we just drew the orbital box diagram, and now we can write out the electron configuration that corresponds to that orbital box diagram. So we're going to use the orbital box diagram in this case to guide us for what our electron configuration is going to look like. So I'm just going to go back and forth between the previous slide and this one just to assess and again, explicitly connect our electron configurations to the orbital box diagram. So we started here, right? You are here. We fill the electron from the lowest energy all the way up to the highest energy. So we are going to start with the 1s orbital, and we're just going to work our way up. So there are 2 electrons in the 1s orbital, so we are going to write 1s2. Then going back, we can see there are 2 electrons in the 2s orbital, so we are going to write 2s2. And here's where the first sort of distinction between how explicitly clear the orbital box diagram is and the shorthand notation of the electron configurations. According to the orbital box diagram, we can see explicitly, right, there are 2 electrons in each of these individual 2p orbitals. However, with the notation that we use for the electron configurations, we actually lump all of the orbitals in a particular subshell together. So next up in the electron configuration, we're going to write 2p6. Right, there were 2 electrons in each of those individual 3 orbitals. We sum all of them together for a grand total of 6 inside of the subshell. So that's the big difference between the orbital box diagram and the electron configuration, aside from the fact that you draw boxes in one and don't in the other, is that the electron configuration notation is really going to lump everything that is degenerate or has the same energy together into one quick notation. All right, well, after the 2p, we can move on to the 3s. We can see there's only one 3s orbital. Again, 2 electrons inside. 3s orbital, 2 electrons inside. And last but not least came the 3p orbital, right, going back to the box diagram. There was the 3p orbital set, which with each of these 3 individual p orbitals inside. And inside of those boxes, we can see a total of 3 electrons. So when we write out our electron configuration, we're only going to write a 3 here, since this 3 represents how many electrons are in the 3p subshell on the whole. All right, and this is our electron configuration then for the 15 electrons inside of phosphorus. So whether we are writing out the electrons in the form of the AUFBAU principle sort of notation, the write that vertical energy diagram, or if we're drawing them in the form of the orbital box diagram, or if we're writing the electron configuration like this, the information that is being conveyed is the same. We have electrons in, or a certain number of electrons in each of these subshells as they build up around the nucleus. Now in chapter 2, we talked about the predictive power of the periodic table when it came to being able to count atoms. The periodic table can also be used as a roadmap to tell us what the electron configuration is for a particular atom on the periodic table. So the modern periodic table is a roadmap that is arranged by atomic number, where the atom with the lowest atomic number, hydrogen, with only 1 proton comes first, and each of the additional atoms afterwards, we add 1 proton and we add 1 electron in their neutral forms. Now the periodic table, if you've ever wondered why it's shaped the way that it is, why it seems to be so chunky, why it's not just a nice even list, is because the table is shaped by the electron configurations of the atoms themselves. And so each of the chunks of the periodic table we refer to as a block. And these blocks specifically correspond to the subshell in which your final electron is placed. For example, phosphorus, which on the periodic table is right here, we just wrote out its electron configuration. And in fact, I'll rewrite it just so we're explicitly clear. It was 1s2, 2s2, 2p6, 3s2, 3p3, and wouldn't you know it, 3p is where the last electron in this atom was placed. And the atom on the periodic table is in what we call the p block. Each of the elements that is present here inside of the p block, their last electrons are also p electrons. And the same thing can be said for the s block, which is here on the left, where each of the final electrons is an s electron. The d block, which is in the center, all of their electrons, or all of their final electrons, are also d electrons. And the f block, which tends to hover underneath the periodic table, each of these elements' last electrons is an f electron. On top of that, or I should say, returning to what I started with, the placement of each element, though, on the periodic table and the shape of the periodic table, we can use as a roadmap to tell us what the electron configuration of the atom is. So let's see how to do that. All right, we're going to keep in line with phosphorus first. I'm going to clean up a little bit. I don't want to erase everything. I want to keep this electron configuration here, but I'm going to remove the circles around the block labels because this slide already, yes, is pretty busy. But like with any roadmap, our journey must start somewhere. And our journey when it comes to using the periodic table is going to start with hydrogen. So we are here. And the reason why we start with hydrogen on the periodic table, first of all, it's listed as number 1, so that's a great place to start. But 2, the only electron that's placed inside of hydrogen is a 1s electron. And as previously stated, we always start with the 1s electron. All right, so the labels that are present here, not just on the side of the s block, but also the d block, the f block, the p block, tell us where we are and where we are going as we use the periodic table as a roadmap. So if we're starting with hydrogen, we are currently starting in the s block, and specifically we are starting in the first row of the s block. This symbolizes that as we start moving from left to right, we are going to be adding electrons into the 1s subshell. And our goal is to make it from hydrogen, from point 1, all the way down, all the way across to phosphorus. So we're going to work our way there. So we add 2 electrons into our 1s subshell. And now as we look to the right, because we read the periodic table, we follow this roadmap as how we, at least in the West, read books from left to right, we can see that there's nothing here. What this tells us is that this line is done, and we must now return to the left and start on the next line. You are now here. We are filling the 2s subshell next. This, how we know this is the 2s subshell is because we're still in the s block and we are in the second row of the s block. So after the 1s comes the 2s, and we have to, in order to make it through this particular section of the periodic table, we must place 2 electrons inside of the 2s subshell, which we're just putting the pieces together here since this is, it's kind of filled with dramatic irony since we already know what the electron configuration of phosphorus is. We're just kind of following along, putting the pieces together. We can see that we've already done exactly that. We already knew that there should be 2 electrons inside of the 2s orbital. It's just now we can see how the periodic table is telling us the exact same thing. As we start from our starting position and slowly work our way to phosphorus, we got to place 2 electrons in the 1s orbital first, and then we place 2 electrons in the 2s orbital next. After now the 2s orbital has been filled, we follow along the periodic table to the p block. This is what comes next. Now notice that the p block does not start with a 1p. There is no such thing as a 1p orbital. We've discussed this already. The lowest orbital that you can have if you are working with a p orbital is the 2p orbital. And so that's why the p block starts with a 2p instead of a 1p. Well, as we are following along, right, we're making a journey, we're following this road trip, we're following the map from X all the way to, or from where we're starting from, X marks the treasure, we're trying to get all the way to our phosphorus. We've now entered the 2p subshell. And we need to place 1, 2, 3, 4, 5, 6 electrons in the 2p subshell until we can move out of it, right? As we move our way across the periodic table, what this is telling us is that we have to place 6 electrons in our 2p subshell, and then it is filled. Check, filled. Now, as we look again to the right, there's nothing here, which means we have reached the end of our line, and we're gonna have to circle all the way back to the left. The next row, we can see we are back in the s block. Our next orbital has to be an s orbital. And the next s orbital, since we are 1, 2, 3 rows down, is the 3s orbital. We place 1, 2 electrons in the 3s orbital. As we can see, we have already done here 2 electrons in our 3s orbital. And we again are just following our roadmap. Here's us on our little journey, kind of walking all the way across to now what is next is the 3p. We re-enter the p block. And the number of elements, or the number of squares we have to pass through, the number of columns that we have to walk through, tells us how many electrons get placed in that subshell. And so from aluminum to sulfur to phosphorus, we have to place 3 electrons in the 3p subshell, and boom, we've made it to phosphorus. And so now we can see that the periodic table, if we were to start from scratch, would give us the exact same electron configuration as what we have already determined using the orbital box diagram method. So the two are going to work together, and the periodic table is actually a really great place to go to try and like jump ahead to see where you're going to be going, to use this to tell you if you don't have any type of energy diagram, what orbital comes next. All right, well, let's say we've made it to phosphorus, and then we get a phone call, and our phone call says, oh, well, I think I need you to now travel to platinum for work, right? Suddenly in this example, we're now like a traveling salesman or something. So we need to go to platinum. That's where our next stop is. Well, there's no reason to reinvent the wheel. I mean, we've already made it to phosphorus, so let's just keep going from here. I mean, we could start the journey all over again in hydrogen, and I could repeat myself all the way up until phosphorus, but up until this point, the journey is still the same. We're always going to start with the 1s, we're always going to move into the 2s next, the 2p after that, so let's just pick up where we left off. We are currently in phosphorus. Our new goal is to get to platinum, which is this element that is circled down below in the D block. It's going to be a pretty long journey, so in fact I'm going to rewrite my electron configuration so far down below just to make sure I have space for everything. 1s2, 2s2, 2p6, 3s2, and we are currently in 3p3. Well, since we need to get to platinum, let's just finish off this row. We have currently added 3 electrons to the p subshell. Let's add another, right? 1, 2, 3. We now have a total of 6 electrons in our 3p subshell. We have finished off this row, and we must circle back around to the left and start with a new row. We re-enter the S block for a 4th time, meaning that we are now in the 4s subshell. 4s. We have to add 1, 2 electrons into this 4s subshell as we work our way across the 2 columns. 2 goes up in the superscript here. And here's where things really start to get interesting. Next up, we are entering the D block. But not just any d orbital, we are entering the lowest energy d orbital that is possible, the 3d. Right, so there's a reason why there's no 1d, there's no 2d. Those are both invalid sets of quantum numbers. They are not real. 3d is the lowest that we can go. And so it throws some people off sometimes that we write 4s2 and then 3d after that. Like, why is it that the 3d comes after the 4s, right? Why is this the order? Well, the ordering, again, mirrors the relative energy levels of these orbitals. If we would return back to the AUFBAU principle illustration, where the energy orbitals, or the energies of the orbitals were listed like low down below, high up on top, 4s actually came before. It's lower in energy than the 3d. So we list the 4s orbital first, and the periodic table actually reflects that and tells us the 4s comes first. The d comes after the s. And the 3d, again, is the lowest energy possible for the d subshell. So we put that first. No 4d, no 2d, it is the 3d first. All right, so how many atoms do we have to walk across? How many squares here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 different electrons that must be placed inside of the 3d subshell, and now we are currently standing here. 10 electrons. Well, we can see as we exit the d block, we now must re-enter the p block for the third time. This is going to bring us into the 4p subshell. 4p. There are 1, 2, 3, 4, 5, 6, always 6 electrons at most that can be placed inside of any p subshell. So I hope you're starting to see that pattern. We come to the end of the line and again, start anew. We are nearly there. Platinum is still like at least another row away. But as we enter the 5s, again, seeing the pattern, there's always 2 electrons at most that get added into an s orbital, which we can see exactly reflected in the periodic table because there are 1, 2 squares that we need to pass through. After 3d comes the next highest in energy d orbital, which is the 4d. And much like before, there are 10 columns or 10 boxes that we must walk through, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 boxes across. 10 electrons get placed inside of the 3d subshell. After this, we move back into the p block. Again, 5p follows next. 6 electrons across, 1, 2, 3, 4, 5, 6. And we come to the end of another line. So we've made a pretty long journey so far, but we are approaching the end of the road. We have to loop back around to a new row for the last time. We now enter the 6s. We are getting pretty big here. If we were to illustrate what this atom actually looked like with all of the orbitals superimposed, it would look like a crazy mess. There are so many orbitals present. So this is why, again, we use our electron configurations. Even though it may, so far just looking at the periodic table, look like a bunch of like scribbles, complicated kind of like road work, like signage that's going on here. But once you get used to using the periodic table like this, it, I promise you, becomes second nature. All right, so after the 6s, we can see that we don't actually follow to the 5d. We don't go back to the d block right away. If we follow our arrow down from here, we can see this is exactly where the f block is supposed to be inserted into the periodic table. The reason why we don't print periodic tables like that, I mean with everything all in a row according to the electron configurations, is because the periodic table would be too wide. I mean, it's a printing logistical error. And so we pull the f block out, have it hover underneath the periodic table, and as a result of that can sometimes forget that it actually belongs in the periodic table. All right, so if we place the f block though back into the periodic table where it's supposed to be, we can see that the 4f orbital follows after the 6s. All right, why 4f? Why not 5f? Why not 3f? Why not 6f? Wouldn't that make sense? Well, the f orbitals are what come next, according to our energy diagram, and the reason why it's a 4f is because 4f is the smallest of the f orbitals. Again, we talked about this in chapter 3, part 4, where we were discussing the atomic orbitals and all of the different quantum numbers that went along with them. 4f is the lowest energy f orbital, and here is where the f series now gets introduced. All right, how many electrons do we place inside of an f shell, or an f orbital? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 electrons. 14 electrons get placed inside of the 4f subshell. Now that we are at the end of the F line, where do we go? Well, since the F block is actually shoved right here in the periodic table, after we end with YB, the end of this row, we're going to circle back around, circle back around to the 5D. We circle back to the 5D. We are in the home stretch. Platinum is in sight. The road trip is almost over. 5D comes after 4F. 5D comes after 4F. And we will move 1, 2, 3, 4, 5, 6, 7, 8 electrons over. And once we have made it to 5D8, most assuredly we are in the D block. Our last electron was a D electron, and our journey is complete. The electron configuration for platinum can be seen here, and we constructed it using only the periodic table and our previous knowledge about what it means to write an electron configuration. That took a long time though, didn't it? I mean, that was a long electron configuration. So is there a shorthand of the shorthand of the shorthand that we can write? Oh, you know that there is. We call these noble gas electron configurations. It's kind of like when you give directions, and when you're giving directions to a friend, I mean, you're not going to say, okay, well, you start from your house, and then you drive down your driveway, and then you drive down this street, and then you drive down that street. Like, you're going to give your friend a familiar road mark, a familiar landmark, and then you're going to start giving directions from there. Like, oh, hey, do you know where the Chrysler building is? Oh, well, from the Chrysler building, then you drive north by a block, go east by a block, etc. The noble gas configuration kind of follows the same method. We're going to start with something that's a familiar road mark, a familiar landmark, and then go from there. All right, so the two definitions that we need to lay out before we actually start writing out these noble gas configurations are the core electrons and the valence electrons. These are two terms that get used so much in chemistry, so important. The core electrons. These are the electrons that are in the filled inner shells. These are going to be the things like the 1s and the 2s, the ones that are really buried in close to the nucleus. These are found to be not involved in chemical reactions. They're just buried too deep. The valence electrons, on the other hand, these are the ones in the unfilled outer shells, the ones that are going to actually influence the chemical reactions. Valence electrons are what give atoms their specific character. So how we can determine which electrons are core and which are valence comes down, again, to the electron configuration, and we can use the noble gas method to also very quickly illustrate which electrons are core and which are valence. All right, so we're going to illustrate the noble gas configuration for platinum, right? The same element that we just illustrated, its incredibly long electron configuration, and now we're going to show this shortcut method, right? Again, shortcut of a shortcut of a shortcut. All right, so we're gonna go back to our diagram, and we're gonna clean it up a little bit. Keep in mind, again, 5D8, our final resting place for this last electron, kind of keep that in the back of your head, but I'm gonna clean all of this up. Boom. All right, so what our landmark method is, what the noble gas notation does, is instead of starting at hydrogen every time, right, you're not gonna start giving directions from your friend's driveway, you're gonna find a familiar landmark. And so what you're gonna do is, instead of starting with hydrogen, instead of starting at the very beginning, we are going to backtrace our way to the most recent, the closest nearby noble gas. So in this case, if we start at platinum, work our way back through the 5D, through the 4F, through the 6S, and then back up the next line. So we're reading backwards from right to left, and then from bottom up, the closest noble gas that we found is xenon. What this means is that if you are writing your electron configuration for platinum, in much the same way you're giving directions, you're going to tell someone, oh, well, start from xenon. That's your landmark. That's your Chrysler building. You're going to start with xenon. And from xenon, well, then you're going to hook a left at 6S. you're going to follow through with the 4F, and then you're going to finish with your 5Ds and end exactly where we thought that we would end. It's just instead of writing everything up until the end, we've now lumped anything that can be contained within this noble gas within this noble gas notation. Another way to think of this more explicitly in terms of chemistry and writing out electron configurations is that the xenon here in brackets is shorthand for xenon's electron configuration. And the reason why we pick the noble gases for this particular shorthand method, like why we don't just, why don't we just pick osmium since it's so close, or even better, why don't we just write platinum in brackets? Well, the reason why is because these noble gases, this last column of the periodic table, which we're going to be talking more about chemical properties in the next lecture, but suffice to say, what makes the noble gases special is that they are chemically inert. They don't react with anything. And so it's really nice to think of your noble gas configuration as being your core. These are the electrons on the inside of the atom that are not going to react. Because if we were to look at xenon on its own, with the same set of electrons as what we've just shorthanded here inside of platinum, it doesn't react. And so anything that is wrapped up inside of your noble gas in this noble gas configuration is going to be the core. So we're coming back to this slide. I'm going to rewrite xenon 6s2, 4f14, and then 5d8, where your core electrons, these ones in the filled inner shells that are not going to be involved with chemical reactions, are these electrons right here. This is the core. Your valence electrons are in the unfilled outer shells. So something important to note here is that we do have a couple of filled atoms, or not filled atoms, filled orbitals, right? The 6s2 is filled, the 4f14 is filled, the only subshell that remains unfilled in some way is the 5d. So does that make the 5d your valence? Is everything that is not listed inside of the core valence, like are the two mutually exclusive? Is the thing that is labeled as the most outer shell, which would be the 6s with the largest quantum number n, is this your valence? Like, what does it mean to be valence? There are a couple of different ways that we can think about this, right? So in parallel to like day 1 or day 2, when we were talking about classifying matter and how some pieces of matter, all depending on how you define them, could have different classifications, the same kind of thing can happen here. Each of these sets of electrons, the 6s2, the 4f14, and the 5d8, all give platinum its unique characteristics. Each of these could be considered to be valence in some way. If we are, though, considering the ionic characteristic of platinum and which electrons are going to be the most reactive first, that award goes to the 6s2. And so if we were to label which of these sets of electrons is the most valence, the 6s2 is what we would consider kind of conventionally to be the valence electrons. Well, if the core is the xenon core, and the valence electrons, by like technical definition, by conventional standard, are the 6s2 electrons, what does that mean about the 4f14 and the 5d8 electrons? Well, these will sometimes also be referred to as valence electrons because they're technically not in the core. Sometimes they will be referred to as kind of core because they're not super reactive. The way that I refer to them, just to admit that they're kind of in this gray in-between zone, is I call them pseudo-valence. Right? It just kind of feels better to, instead of trying to like pick these electrons up and put them in one of the two classifications that don't really fit, right? Again, they're not really core because they're on the outside, but they're not really valence because they're not super reactive. We're just going to call them pseudo-valence. They're sometimes reactive. They're more reactive than the core electrons for sure, but they're not technically defined. They're not conventionally defined to be valence because they're not in the outermost subshell. Again, that would be our 6s. We have our core, we have our valence, and we have our pseudovalence. The cores are again going to be on the inside, not really defining the reactivity or any like specific properties of the atom. It is going to be these valence and then in combination, right, additional flavorings from the pseudovalence that are going to give us the real reactive characteristics for each of the elements on the periodic table. So here we come at the end of the day to another example problem. After all that we have talked about, after all of the diagrams and the rules and the shorthand, it now comes time to test how well this has sunk in. Provided the electron configurations below in their noble gas notation, what neutral elements are these? Use the periodic table as a roadmap. See if you can't find what the label is for each of the elements that have these particular electron configurations. All right, welcome back. Let's check out a periodic table, right? The nearest one that I have that I can show you is this. And again, I'm just gonna clean it because I need it to be fresh to use. All right, so our first electron configuration, just to come back to our example problem, we're gonna start at argon. We're gonna hang a left at 4s2, and we're going to move 4 places over in the D block, in that first row, the 3D row. All right, so we're gonna start at argon. We are here. We're gonna cruise on right through the 4s, and we're going to move 1, 2, 3, 4 positions into the D block. Here we can see the element that we have landed on is chromium. Therefore, the element that has this electron configuration in its neutral form is chromium. Right, so using the periodic table as a roadmap is a really handy tool. Instead of having to write out electron configurations like from scratch and making second guesses, the periodic table is good for so many powerful things. All right, so let's look at our next example. We have krypton. We're going to then move on through the 5s, and then into the 4D, 9 positions over. So we're going to start at krypton. We're going to move through the 5s and then jump 1, 2, 3, 4, 5, 6, 7, 8, 9 positions over. And we can see that this corresponds to the element with the symbol Ag. And the symbol of Ag corresponds to the element of silver. So krypton, 5s2, 4d9, this corresponds to the element of silver. All right, last but not least, we can see that there's another little bit of a doozy. We're moving through the 4f subshell again. So we gotta start at xenon, cruise on through the 6s, 14 of the 4f electrons, 10 of the 5d positions, and we're going to finally rest in the 6p subshell. All right, so let's start with xenon. Cruise on through the 6s. We're gonna move through all 14 positions of the 4f. We're gonna move through the entirety of the 5d, and now we can see up next is the 6p. We move 1, 2 positions over, and lead is where we find our the element that we are curious about. So the element with this particular electron configuration in its neutral form is lead. All right, so if we give you, or if you come across some particular element name, you should be able to write out either the total electron configuration, the noble gas configuration, draw the orbital box diagram following the 3 rules that we've talked about, any of the above. Or if I give you that information, you should be able to use the periodic table to identify what the element is that we are actually working with. And that's been a lot, so let's call it a day. All right, so here we have a couple of example problems pertaining to electron configurations and using the periodic table as that lovely roadmap. Now, I will give the disclaimer because, of course, for every rule, there is at least one exception. Figure 4.5 in the text will supply all of the valence electron configurations for the elements, so not the core, but it will give you all of the valence and pseudovalence, and all of the exceptions to the rules. Now, we will be talking about how to predict exceptions to the rules in the next coming few lectures, but we're not quite there yet. However, there will probably end up being 1 or 2 questions on the homework assignment that just, without me either realizing or because I'm trying to be a little bit tricky, will list some of those exceptions. So when in doubt, check out figure 4.5. It will give you the information that you need, and you can also use it to double check your own configurations if you're writing them from scratch. All right, if you have homework, do your homework, and class is dismissed.